While your tissues are hardening in that plastic, you can get ready to make sections of the tissues by preparing glass knives. Now, if you were in a controlled laboratory situation, you'd probably have a knife making machine. These cost about $2,000 and they're big and quite bulky. We obviously don't want to carry those around in the field. We're going to go a little bit old school and use the techniques that were in existence before the invention of these glass knife making machines. We're going to score and break glass by hand. You'll use glass made specifically for histology, and you'll lay those strips out on a template that shows you how to score them. You'll need a ruler. And you see that the ruler on the back is cork lined, and that keeps the ruler from sliding around the glass when you're cutting it. And you'll need a diamond scribe to score the glass. And you'll need some glass breaking pliers. You can see I'm not going the whole way down here. You want the glass to actually snap right at the edges. That's going to give you a nice sharp blade. Don't put too much pressure down when you're breaking the glass, so this has got a screw right here that limits how much the pliers can close. So you tighten it down until it's touching the glass, pull it out and back it off about a half a turn. And that lets you put just the right amount of pressure on it. Line up your pliers with the straight scores to make a series of 1-inch squares. And then line up the pliers with the diagonal scores to make the cutting edges. Store the glass knives in this glass knife holder.
Here we have some of the glass knives that Ken broke. Some of them are going to be usable, some of them are not going to be usable. First of all, you want to look for the ones there should, normally on both glass knives there should be what I like to call the foot, and then there should be a sharp side up top. You can see this one has 2 dull sides, or 2 feet, so we're going to set that aside because it's not good for anything. When you have one that has 2 feet, you probably have one that has 2 sharp ends. A little dangerous, but it is usable, and particularly that edge right there has a nice swirl in it. It's fairly straight across there, so we're going to go ahead and save that and put that in our knife box. It's very important that you don't touch the tip. You can cut yourself. The other thing is you can nick the blade, which will cause imperfections in the sections. It's also a good idea just to handle them from the sides, because even the oils on your hands can make it difficult for the sections to slide down the blade. That edge right there, you can see there's a nice swirl going up from your left to right. That would be a decent cutting edge right there. Here's a normal one. It's got a foot that's dull. Okay, so that's going to be sits at the foot of the microtome, and then the top there, you can see it's a little slanted, but this is still usable depending on how wide your stub is that you're sectioning. Can still be usable, so we'll stick that in there. Oftentimes, I don't know whether a knife is good or not until I start sectioning with it, so I tend to put everything in there that looks like it might be good, and then I might throw some out as I'm sectioning. There's a really nice blade there up top. You can see it's straight. There's a nice swirl in it through the glass. That's probably going to be really good at giving us nice clean sections.
Then get your microtome ready to make sections by installing a glass knife. After that embedding solution is properly hardened, you're going to need to get your subsamples out of the beam capsules and get the tissue stubs or tissue blocks ready for sectioning.
After we have hardened our resin inside of our beam capsules, we put it inside the dry box, which has some desiccant in there, acts as a desiccator. And we're going to open that up, and here are our completed beam capsules with our hardened stubs in there. So we're just going to pop a few of those out, and now we have to cut those out of the capsules so that we can put them on the microtome and actually begin sectioning them. So all we do is get a couple razor blades, real sharp. You trim off the end, making sure you don't trim off the tag itself, and then do a lengthwise this way, and then kick out to either side, and then that will help you pull out your stub. Okay. And then we'll pull that specimen out. There you go. Okay. So again, you can see there's a conical tip. So we're just going to trim off the end of that tip with a razor blade, so that as soon as we start sectioning on there, the microtome will be within the gonad. It's going to make the process a lot faster. I'll trim up all 15 of our embedded stubs in the same way, and then after we do this, we're going to place them back in the desiccator to continue drying out and hardening, because we're in a very warm, humid environment. They tend to be a little bit sticky when they come out. We can actually put this out in the sun, let it sit for the day, and it'll continue to dry out, so the stubs will be hard enough to section.
And we're finally ready to start cutting really, really thin sections of the gonads so that you can examine them under the microscope. Later you'll take that stub out of the desiccating chamber, look at the number on the label, and record that number on a glass microscope slide. Prepare your slide to receive tissue section by placing 10 drops of water on the slide. Place the stub into the microtome.
Okay.
Then move the glass knife into position so that it's just touching the end of that stub. Lock the knife into place, and then you can begin sectioning. Now this takes a little bit of coordination, so we're going to slow it down so you can see what's going on. Notice that Ross is using both hands in this process. His right hand is turning a crank that's moving the stub up and down. His left hand is turning a dial that's moving the knife progressively closer to the specimen. So the right hand cranks, left hand turns. Right crank, left turn. Right crank, left turn. When you have a good section, remove it from the microtome and float it on one of the water drops.
And then we'll go back and get another section. Now, we don't want to get the same exact section, so we're going to trim for a little while, just letting the microtome do some cutting. So we're going to be further down in the piece of tissue when we collect our next section. So discard 15 or 20 sections, because each section's about 6 or 7 microns. We know how far we've gone in the gonad. And then we'll collect another one.
Continue sectioning. And do that until you've filled up all 10 of the water droplets on the slide.
Bottle caps, bottle glass, solar panel glass.
One of the challenges of working in a tropical open-air environment is the high humidity will eventually make those stubs gummy and difficult to section. You can reconstitute or reharden those stubs by putting them back in the desiccating chamber, waiting a little while, and then bringing them back out, putting them back on the microtome, and you'll have a much easier time with additional sectioning.
Now eventually, this knob, as the fine adjustment, will bottom out, and you'll have to reset the whole contraption. So we just back this off, pull it off, unscrew the coarse adjustment, and then unscrew the fine adjustment very quickly until the knob is all the way to the reset position.
You'll need to gently dry those wet slides, and in a controlled laboratory situation you'd probably use a slide warmer for that. Here we show you the improvised solution we use in the field. Take those slides that you've been making and dry them by putting them onto a warm surface. Here we're using nothing more than a cast iron baking dish placed out in the hot sun. And you don't have to wait for a sunny day to do your work. You can pour a little alcohol into that dish and start a fire, let it warm up a little bit, and then turn the dish over to put the fire out.
Check the slides, make sure it's not too hot, otherwise the slides will crack. Then we can place our slides on the drying plate like so.
Next, you're going to stain those slides so you can see what's going on in the gonads. And this is the last step that you'll take before you examine the prepared slides. Next, you'll stain those slides. And rinse off the excess stain. And put those stained slides on the warm surface to dry again. Organize your stained slides in a slide box. And then you'll examine your slides on a microscope. Here you'll determine the sex and the reproductive state, and you'll record all that information on the data sheet. Now we're going to spend some time talking about what you are going to use as evidence of maturity. We'll talk about the males first because that's the simplest scenario. All you need to find out is whether there are sperm cells with tails present in the gonads. This is an example of an immature male. These developing gametes shown inside the circles do not have tails. It's going to be a little bit easier to see what I'm talking about in the next slide when I'll show you an example of sperm with tails. And if you look inside the circles, you'll see those fine lines, and those are the tails of the sperm. So this specimen would be scored as a mature male. And it's that simple for the males. Now things get a little bit more complicated for the females. You'll have to evaluate whether the oocytes or the eggs have reached stage 3 or 4, or whether you're seeing post-ovulatory follicles. Now we're going to go through some examples of what each of those stages look like, as well as some examples of what oocytes or egg stages representing immature females would look like. And here's a list of the characters for each of those oocyte stages, or egg stages. What you'll be looking for is the diagnostic features, which are listed in bold. These are the things that define what those egg stages are. Now don't get worried about this big list. We're going to go through and look at examples of each of these stages in individual slides next. The arrows in this slide point to the developing gametes in an ovary. These are oocytes or eggs. The diagnostic feature of these is that they stain uniformly dark. Now, when you look at the slides coming up next, you'll also see that all of these oocytes are very small compared to all of the other stages. The other thing that I should point out here is that every single oocyte present in this ovary is in stage 1. The yellow arrows in this slide point to stage 2 oocytes. These also stain uniformly darkly, but they're getting a little bit bigger compared to those stage 1 oocytes you saw in the last slide. What you'll find in these stage 2 oocytes is some non-staining white spaces that represent lipids. We consider ovaries that have only stage 1 or stage 2 oocytes to be immature individuals. Now the yellow arrows are pointing to stage 3 oocytes. What you're going to see are a bunch of small, brightly staining circles, and these represent vitellin, or the yolk proteins. We consider stage 3 oocytes to represent mature individuals. Technically, they're not mature yet, but they will be mature very soon. Stage 4A oocytes are going through the final process of maturation. What you'll see in these oocytes is that the yolk protein has coalesced into larger and larger globules. Stage 4B oocytes are just about ready to be spawned, and here you're going to see that all the yolk protein is just a single mass. Often there will be non-staining portions of the cell right around the periphery. The other thing that you should notice is that the shape of these cells is oftentimes very irregular compared to the round oocytes that you've seen in the previous stages. And finally, just after spawning, you may see a remaining structure called a post-ovulatory follicle. Now again, because this fish has spawned, it would be considered to be mature. Post-ovulatory follicles, or POFs, are about half the diameter of what you saw in stage 3 oocytes. The other thing that you'll see is there's a lumen, or basically an empty space, in the middle of that post-ovulatory follicle. That takes care of all the identifiable stages of male and female gonads. There's a couple of more categories that you may have to use. The first is undifferentiated. This means that you have a gonad, but the sexual characteristics haven't developed yet. In other words, you can't tell whether this is a male or a female. And transitional is the other category that you may have to use. This would be applied to species that change sex as a part of their normal development, and in these gonads you would see mixtures of both male and female gametes. And I want to emphasize here that you should record the egg stage. You won't use this information for determining size at maturity, however the information will become very important later on when you're choosing specimens to use for a length fecundity analysis. Now let's talk about how we're going to determine size at maturity. There's a couple of approaches to this. One is to report the length of the smallest mature individual, and this is called LM oftentimes, or L-min. This is not the measurement that we emphasize, but it is a good idea to report it. The measurement we're after is called L50. This is the length at which, if you took a bunch of specimens of the exact same length, 50% of the individuals would be mature. And I should emphasize here that you will report size at maturity for both males and females separately. Let's take a look now at how you calculate L50. This concludes Module 5. I'd like to take this time to thank our funder,